We're going to learn a new technique that's used to integrate some integrals involving rational functions of sine x and cosine x. Okay, so for example, these three integrals, these are rational functions of sine x and cosine x, and we don't have any standard techniques for integrating these yet. All right, let me mention that there are many integrals involving rational functions of sine and cosine, which we do know how to integrate. And let me just give you some examples of some of those. Okay, for example, let's say we know how to integrate something like this. 3 plus 5 sine x in the denominator and cosine x in the numerator. Okay, this is just a log integral. The derivative of the denominator is 5 cosine x, and we have cosine x over here. All right, so this would be 1/5 ln of the denominator. Or let's say we had something like this. 1 plus sine x cubed in the denominator and cosine x in the numerator. Okay, so this is a simple u substitution, putting u equal to 1 plus sine x reduces this to the integral u to the minus 3 du. Okay, and we know how to continue that. Just one more. We saw an integral like this. Came across this a couple of times. The way we integrate 1 over 1 plus sine x is we multiply top and bottom by 1 minus sine x. That's like a trick for integrating this. All right, so these are three integrals which don't require the technique that we're going to learn today. Here's what we have to know for our technique. The basic substitution is u equal to tangent x over 2. And we'll show that tangent x over 2 using some trig identities is equal to sine x over 1 plus cos x. So if u is equal to tan x over 2 or this expression, then we'll be able to show that cosine x is equal to this, 1 minus u squared over 1 plus u squared, sine x is equal to 2u over 1 plus u squared, and dx is equal to 2 du over 1 plus u squared. So we're going to put cosine x in our integral equal to this expression, put sine x equal to this, put dx equal to this, and end up with some rational function of u that we can hopefully integrate. So we'll go straight to an example, and later, after we do one example, then we'll explain this technique. All right, so let's look at this first example. The integral of 1 over 1 plus sine theta plus cos theta. D theta. All right, so what we're going to do is we're going to put, actually I would rather use, instead of theta, let me just change this to x. Okay, just since we're using x in the box above. So let me do that. Okay, so I'm just changing my variable to x. All right, so we're going to put sine x equal to this expression and we're going to put cosine x equal to this expression. And we're going to put dx equal to this expression. All right, now let's multiply this denominator times this denominator. Okay, and that will simplify things. All right, so let's do that. Okay, so this is equal to So here we have, we'll put 2 du in the numerator. And here 1 plus u squared times 1, that's 1 plus u squared. And then 2u over 1 plus u squared times 1 plus u squared, that's just 2u. And then 1 minus u squared over 1 plus u squared times 1 plus u squared, that's 1 minus u squared. All right, so these two u squareds cancel, and we have 2 plus 2u. And we can divide top and bottom by 2, so we have just du over 1 plus u. Well, that's obviously a log. All right, so that's equal to the log 1, absolute value 1 plus u. And then we could write that we have to substitute back. So u is equal to tangent x over 2. Or we could write the expression for u that involves sine and cosine, if you like. We could write ln absolute value 1 plus sine x over 1 plus cos x. Okay, now let's try to understand the technique, why this works. Okay, so let's start with u equal to sine x over 1 plus cosine x, and show that cosine x is equal to 1 minus u squared over 1 plus u squared. Okay, so we're going to start with u equal to sine x over 1 plus cos x. All right, and what we want to do is we want to show that cosine x is equal to 1 minus u squared over 1 plus u squared. So first, square both sides of this equation, and we have u squared is equal to sine squared x over 1 plus cos x squared. Okay. All right, now replace sine squared x with 1 minus cos squared x. All right, that's equal to 1 plus cos x (1 minus cos x). And now let's just reduce this, crossing out one factor of 1 plus cos x from top and bottom. Okay, so that's equal to u squared. And we can now solve for cosine x, which is what we want to do. Just cross multiply, and we have u squared times 1 plus cos x is equal to 1 minus cos x. And multiply through and keep in mind what we want to do is solve for cosine x. So let's put everything with cosine x on the same side. So I'm going to subtract, put this u squared on the other side, and put this minus cos x, bring that over to here. So we have u squared cos x plus cos x is equal to 1 minus u squared. Factor out the cosine x. And now divide both sides by u squared plus 1 to finish solving for cosine x. and we have the expression that we wanted to show. So we've shown that cosine x is equal to 1 minus u squared over 1 plus u squared, and now we'd like to show that sine x is equal to 2u over 1 plus u squared. So again, we'll start with this expression, or this equation, u equals sine x over 1 plus cos x. Let's do that. Okay. So if we have u equal to sine x over 1 plus cos x, we want to show that sine x is equal to 2u over 1 plus u squared. All right, well, we're going to first start by cross multiplying here. So we have u times 1 plus cosine x is equal to sine x. Now replace cosine x with this expression, 1 minus u squared over 1 plus u squared. Okay, add 1 plus 1 minus u squared over 1 plus u squared, and get a common denominator. Okay, so that's under the common denominator of 1 plus u squared, we have 2, and the u squared and the minus u squared cancels, so that's it. So we have the expression that we were aiming to prove. Okay, finally we have 2u over 1 plus u squared is equal to sine x. And that's what we want to show over here. Okay, so far we've shown that if u is equal to sine x over 1 plus cos x, then this is what cosine is equal to in terms of u, and this is what sine x is equal to in terms of u. All right, let's show that dx is equal to 2 du over 1 plus u squared. This time we'll write u as tangent x over 2. So we'll say, well, if u is equal to tangent x over 2, this time we want to show that dx is equal to 2 du over 1 plus u squared. So we're going to solve for x in this equation. So we'll do that. We'll write x over 2 is equal to arctan u. And now just, and then let's say multiply by 2 arctan u is equal to x. Now differentiate both sides, and we have dx is equal to 2 over 1 plus u squared du. Okay, and that's what we wanted to show. Okay, of course we haven't yet shown that sine x over 1 plus cosine x is equal to tangent x over 2. So that we'll show that next. Okay, and then we'll be done showing that all of these equations are true. Okay. So we want to show that tangent x over 2 is equal to sine x over 1 plus cosine x. All right, well, remember first of all, we know that tangent x over 2 is equal to sine x over 2 over cosine x over 2. Now let's square both sides, so let's just square everything square this and this and this. And now let's use our half angle formula. Sine squared. Okay, so that's 1/2 1 minus cos x. And here cos squared x over 2, that's 1/2 1 plus cosine x. Now multiply top and bottom here by 1 plus cosine x. Okay, so let me rewrite this. The 1/2s cancel, and we have 1 minus cos x over 1 plus cos x. And we're going to multiply top and bottom by 1 plus cosine x. So here we have on top 1 minus cos squared x. And on the bottom we have 1 plus cos x squared. And of course this is sine squared x. Alright, so we get tangent x over 2 squared is equal to sine x over 1 plus cos x squared. And now just take the square root of both sides and we have what we're trying to show. We wanted to show that tangent x over 2 is equal to sine x over 1 plus cosine x. Okay, so now we're done showing all the pieces of what's in this blue box over here. So we're ready to use these substitutions to solve another integral involving a rational function of sine and cosine. Okay, now we're ready to do an example. We already did one example, but that was before we understood the technique. Now that we understand why these are true, we'll do another example. This one looks similar to the one we did before, but actually works out to be quite different. Alright, so we're going to assume that we're going to do the substitution u is equal to sine x over 1 plus cos x. Alright, so this is what cosine x is equal to, and this is what sine x is equal to, so let's do those. Let's substitute. And we have for sine x, we'll put 2u over 1 plus u squared. And for cosine, 1 minus u squared over 1 plus u squared. Oh, somehow I got 2d. Okay, I got rid of one of those dx's. Alright, and then we know that we have dx is equal to 2du over 1 plus u squared, so let's put that in as well. And now we'll multiply top and bottom by this denominator, 1 plus u squared, and we get 2 on top. And here we get 1 plus u squared, plus here we just get 2u. And here we get minus, be careful with signs here, 1 minus u squared du. Alright, let's simplify this. Let's see, we have 1 plus u squared plus 2u minus 1 plus u squared. Okay. Okay, so we have a 2u squared. And the 1 and the minus 1 cancel, and we have plus 2u. Let's divide top and bottom by 2. So we have u squared plus u. All right, now let's factor the denominator. And we see this integral is done by the method of partial fractions. All right, I'm not going to go through the partial fractions technique. I'll just go straight to the breakup of 1 over u plus 1. All right, so I'm just going to tell you that this is equal to, and you figure this out using partial fractions, this is equal to 1 over u du minus integral 1 over 1 plus u du. So these are both log integrals. And now we have to substitute back. Okay, so we'll put u equal to sine x over 1 plus cosine x. Or you could have put this equal to tangent x over 2 instead. Either one is fine. We'll do one last example. The integral 1 over 2 minus 3 sine x dx. Okay, so we're going to put sine x is equal to 2u over 1 plus u squared. Let me mention that our substitution is u equal to sine x over 1 plus cosine x. Okay, so that's u equal to, and this is what sine x is equal to. And we know that we saw that dx is 2 du over 1 plus u squared. All right, let's multiply 1 plus u squared through this denominator. So on top I have a 2 du. And on the bottom we have 2, 1 plus u squared, minus 3 times 2, that's 6 u. All right, so let's work this out. So we have 2 du, 2 plus 2u squared minus 6u, so that's 2 du, 2u squared minus 6u plus 2. Let's divide top and bottom by 2. All right, now we check to see if we can factor this denominator. We can't factor it, but we can factor actually using the quadratic formula. Now using the quadratic formula we have u is equal to negative b plus or minus the square root of b squared minus 4ac, that's 5 over 2a. So these are our two roots. So this actually factors over the reals, not over the rationals, but over the reals. So this is actually u minus 3 plus root 5 over 2 times u minus 3 minus root 5 over 2. And we use the method of partial fractions to break this up. All right, let's do, it's actually easier. We'll come back to this. Let's suspend this for a second. It's actually easier to do the method of partial fractions on something of the form, let's say, u minus r times u minus s. Okay, instead of using, in our case, r is 3 plus root 5 over 2, and s is 3 minus root 5 over 2, but just so that I don't have to keep on writing this cumbersome quantity, I'm just going to put r and s here. All right, and so here, let's break this up. I'll put an a here and a b here. Multiply both sides by this denominator.